All right, so the last idea I want to discuss in this short introduction to series is the test for divergence. So as the name says, this is a way to quickly check whether or not your series diverges. It can't tell you that it converges, but it could tell you that it diverges. So whenever you have a series of this format, so again, note that I don't care what's the initial n value, right? What's the starting n value for the sum. For convergence and divergence, I only care about the tail of the series. So at infinity, what happens to the series? And whenever I have something like this, I'm adding an. So that's the general term of the series. And I take the limit of this an only. So I don't have to go through the sequence of partial sums to handle this. Just an itself, I take its limit. If that is not 0, then for sure the series will diverge. Okay? So just imagine, this has a proof, of course. This is a theorem. So it has a proof. I'm not going to give you a proof right now. If you really want to, I can give you a proof on a different video. But the idea is this. If the limit is not 0, let's say the limit is c, right? Let's say the limit an equals some number c when n goes to infinity. Well, then that means for large n values, for very large n, an is approximately c, right? So this will be, of course, you're adding a bunch at the beginning here, but then at the end, it will be just as though if you were adding a bunch of c's, because each an will be approximately equal to c. So you're adding the same number over and over and over again. If that number is not 0, let's say the number is positive, that's going to go to positive infinity because you're adding, say, plus 1, plus 1, plus 1, or plus 2, plus 2, plus 2. So, of course, your series will diverge. Now, a very important and I guess nuance here, a very important nuance on this test is that when the limit is 0, you cannot say that the series converges, right? You don't say that. You say that the test is inconclusive because there are some series that will have limit of an 0 that will converge and some series that have limit of an 0 that will diverge. Okay, so on this first bullet point, you can say for sure that the series diverges when the limit isn't 0. And on the second bullet point, you are adding things that are very small, but maybe they're not small enough. And then you're adding them, and still the sum is getting to infinity. Now, very important to distinguish between these two outcomes. Couple of examples, very simple here. Okay, this first example, this is this series here. The sum from n equals 2 to infinity to n over 3n plus 1. The n equals 2 does not matter to me. I know that the limit of an when n goes to infinity will be the limit when n goes to infinity of 2 to the power n over 3n plus 1. So again, I can divide the top and the bottom of this by n to get that the limit when n goes to infinity of this is calculated this way. And then this is the limit when n goes to infinity of this is going to be 0. So this is 2/3, which is not 0. And so the series diverges. And it's always a good idea to say diverges by the test for divergence. Because the problem is already saying that, I'm not going to write it down. The problem's already saying that I'm supposed to be using the test for divergence. But if the problem that just says determine if the series converges or diverges, then I'll go and say what was the test that I used, because we're going to learn more tests later. So with a similar calculation here, we can see that the limit of an, so again, I'm not going through the sequence of partial sums. I'm just doing this. Very, very likely, very similar, I divide by e to the power n at the top and at the bottom. I'll end up with limit 1 minus 5 over e to the power n over e to the over 1, excuse me, at the bottom. This is 1, which is not 0. So again, the series diverges by the test for divergence. Now on this one, on C, this is the limit n goes to infinity, 1 over n cubed. This is 0. And so when this is 0, the test is inconclusive. Right now, we only know this test, so we're going to stop here. But later on, as we learn more tests, we're going to not stop here. We're going to say, okay, this test is inconclusive. Let me try a different one until I'm told by the problem to stop, or until I'm convinced of what's going on. Okay. And again, I just really want to show, in fact, the series does converge. There's a test called the integral test, and also the p-series test that we can use for this. One stems from the other. But right now we're going to stop and say that the test is inconclusive. This is the only test I'll ask you about in the first sort of few days, initial days of studying series. And I just really want to show you this one, though. The reason why this test is inconclusive when n equals 0, the most convincing way to see that it is by looking at this series. This series is so important that it's given a name. It's the harmonic series, not only because of its mathematical behavior, but also because of its physical behavior. It has to do with the principal frequencies of oscillation in sound. I'm not going to get into this right now, but the idea being that this thing, right, you could think, if you write a few terms, let's say if I try and add up to 5 or something, of 1 over n, this will be plug in n equals 1, and then plus 1/2, and then plus 1/3, then plus 1/4, and then plus 1/5. You see that's a 0.2 right here, super small. And if you really want to add, let's say, more terms, you can actually go to a calculator and ask it to add those for you. And so this last term is a 0.01. It's so small. And if you ask a calculator to add more and more terms, you may be fooled into thinking that this will converge. Even so, the limit of an here is 0. It goes to 0. So you would think that it converges. But in fact, it does not. The easiest way to see why it does not converge is to graph this series. Just imagine it this way. Let's graph the sequence. So at 1, this is, maybe let's use scale a little bigger. At 1, this is 1. At 2, this is 1/2. At 3, this is 1/3, and so on. Put 2 5s there. And if you think about it carefully, each of those numbers that you're adding equals the area of a certain rectangle. So this first rectangle here has area 1. Look at it. It's got base 1 and height 1. Yeah. And if you add another rectangle here, this rectangle will have base 1 and height 1/2, so it will have area 1/2. And then you can do another with area 1/3, and you're already, I'm guessing, following that what's going to happen here is some sort of integral. Because if I look at the function y equals 1 over x now, it's going to go through each of those points because it will coincide with this. So if I graph it, you can see visually that the integral of 1 over x from 1 to infinity, which would be the area under this green curve, dx, will be smaller, will be less than my series. Because the series will be the sum of the areas of all those blue rectangles. stop here for a second to think about it. Keep adding more and more rectangles, they're always overestimating the area under the curve. So they'll have more area than the integral counts for. But then the integral, if you go ahead and calculate it, it will be 1 to infinity, 1x dx. That will be the limit, let's say when m goes to infinity, of the integral 1 to m, 1 over x dx. That's an improper integral. So this is limit m goes to infinity. That's the natural log of m minus the natural log of 1. The natural log of 1 is 0, and the natural log of m when m goes to infinity is going to go to infinity as well. So if the area under the green curve is already infinity, then the blue rectangles have no hope of adding to a finite number because, well, they're even bigger. So I hope this was enough to convince you that the harmonic series diverges, even though it doesn't look like it if you plug into a calculator. And even though, so this diverges even though the limit of 1 over n goes to infinity equals 0. So limit equaling 0 is not enough for me to say that the series converges.